Okay, in that case, let's start with our second lecture. So, very quick review, just one line almost, is that in the last class, we derived the Rayleigh-Jeans formula. So what is the Rayleigh-Jeans formula? It gives me the radiation density around the frequency nu in an interval d nu, and it's given by 8 pi nu squared kb t divided by c cubed d nu, where the factor kbt came from the equipartition theorem. And the fundamental assumption that goes into the equipartition theorem is the Boltzmann factor, and you derive that in the tutorial. So obviously, the Rayleigh-Jeans formula, let me write those words. So the Rayleigh-Jeans formula, diverges as the frequency goes to infinity. So that's why it's called the ultraviolet catastrophe. And the Rayleigh-Jeans black body radiation was an active field of research at the end of the 19th century. A lot of theoretical physicists were trying to find a way to explain this. So of course, since the radiation density diverges, the total radiation, which will be the total if we integrate over all the frequency, I should say the total radiation density, because this is radiation per unit volume, is going to be the integral from 0 to infinity of u nu d nu. And of course, this is infinity, and this infinity, the divergence comes from this n. Okay, so bad news. So how did Planck solve this problem? So the next topic that we will discuss is called the Planck Hypothesis. So before we talk about what Planck did, Planck, of course, was not working in vacuum. He was influenced by other theoretical physicists who were working on the same thing. Not just theoretical physicists, experimental physicists. There were several people involved in the story who were also experimentalists. So one of Planck's friend, his name was Wien, like in Vienna. Wien had derived a formula that was appropriate, that was accurate in the ultraviolet. Okay, so this is basically opposite of the Rayleigh-Jeans formula, where it was inaccurate in the ultraviolet. However, Wien's derivation was based on purely, it was inspired by Boltzmann's idea of molecules that is based on thermodynamics. So one of the things about thermodynamics is that thermodynamics is kind of agnostic about what is the constituents of matter, right? Thermodynamics, it makes a more general statement. So it didn't talk about, the nitty-gritty of the particles or whatever that gave rise to this radiation law. However, Wien's, so this law is called Wien's distribution law. And we don't need the explicit form of the law, but the law is U, the density of radiation at frequency nu, is given by nu cubed times some function that depends on the ratio of nu and t. Okay. In fact, this function was an exponentially decaying function. So this is essential. So we are not going to derive this, but we are going to use this, and Planck used this in his derivation of the blackbody radiation. Okay. So one of the things that Planck realized was that the divergence in the Rayleigh-Jeans formula comes from the KBT part, because you see that this part is independent of the frequency, right? And therefore, as we are integrating the frequency, we are getting more and more contribution. So from the coefficient of the of the equipartition theorem. So what Planck said, that what if it became harder and harder in some sense for the oscillators which model the molecules and the atoms on the wall of the black body? What if it becomes harder and harder for them to reach higher and higher energies if their natural frequency is large? So for the oscillators whose natural frequency is large, what if it's harder for them to reach the higher energies? Okay, so Planck said that this can be achieved if we think of the energies of the oscillator to be given by an integer, a positive integer, times some fundamental unit called epsilon. Okay, and epsilon in principle is a nu dependent quantity. Okay. So this was the idea that led to the Planck distribution. So if this was the case, this is very different from the equipartition theorem. It leads to a very different result, and let me show you how. So now we can ask again, what is the average energy of a mode? So the average energy is then going to be, say, it'll now be n times E times the Boltzmann factor, which is e to the power minus NE by KBT, and the sum now goes from 0 to infinity. So this is basically, instead of an integral where we had KBT here, we now have NE. Okay, and then we have to normalize this. So we also normalize this as we did before. So in the denominator, we have NE by KBT. So now we have to evaluate this average energy. Okay. So to evaluate this, let's introduce a new variable, x. X is defined to be e to the power minus epsilon by KBT. Okay. Then we can rewrite the expectation value of E to be, we can factor out the epsilon, and there's a sum over n goes from 0 to infinity, n times x to the power n. And that is divided by sum from n goes to 0 to infinity of x to the power n. Okay. So this is actually quite easy to evaluate. So first, start with the denominator. So the denominator is an infinite geometric series, the first term of which is 1, the second term is x, the third term is x squared, dot, dot, dot. And you know from your high school mathematics that this sums up to 1 minus x. Okay. So this is the denominator. So what about the numerator? So we can actually derive the numerator from the denominator. So note that we can derive the numerator from the denominator. So the numerator, involves sum over n from 0 to infinity n times x to the power n. But this thing we can write as, we can factor out 1 of the power of x, and then we have n times x to the power n minus 1. I'm not going to write the limits, it's the same limit. And that we could, yeah?
Do we have any condition that x should be less than 1?
Yes, x should be less than 1, but because the exponential, is going to be, has e to the power minus, so it's, yeah, it has to be, less than 1. You're right. Because otherwise, we don't have that, it's like, this is a Taylor expansion of this only when x is less than 1, right? So, which in this case would mean that e to the power minus epsilon divided by kbt, this is a positive quantity, is less than 1, right? So if I now take the logarithm of this, I get minus epsilon by kbt is less than, this is a negative, right? Log of 1 is 0, right? And it is, everything on the left-hand side is positive, like all these quantities, right? So it is true that this is a negative quantity. So that's satisfied, okay? Okay, so now if you come back to this, we can write this as x times the derivative with respect to x of the denominator. Okay. So now we can write this so when we evaluate this, this just becomes x divided by 1 minus x whole squared. Okay, we're just using this result. Okay, so then the expectation value of E becomes epsilon times e to the power minus minus epsilon by kbt, which is this factor, divided by, there will be only one factor of this guy because this guy will cancel one of the factors. So in the denominator, we have 1 minus e to the power minus epsilon by kbt. Okay, so now if I multiply both the numerator and the denominator by the inverse of this factor, then the numerator just becomes epsilon. The denominator, the first term then becomes e to the power epsilon by kbt. Note the sign here, it's a positive sign, minus 1. And this is the average energy that we have to consider for the oscillator whose energies are quantized. Okay. So now the rest of it is we just follow the same logic as before. So before we do that, let's look at the high temperature limit, because at high temperature, we would expect more of the usual classical thermal, result to hold. So in the high temperature limit, where T goes to infinity, we find that E epsilon by kBT, we can just approximate it by 1 plus epsilon by kBT. And therefore, in the high temperature limit, this just becomes kBT, which is the result that we got from classical statistical mechanics. So in the T goes to infinity limit, in the high temperature limit, Planck's result agrees with the classical statistical mechanical result. Okay.
So for it to match the classical result, isn't t goes to infinity a weird assumption or something like?
No, t goes to infinity is not weird because we are just saying that t is large. That's all we're saying. We are introducing a new energy scale, right? Epsilon is a new energy scale. We don't know what it is. Okay. Now, kBt is the thermal energy scale, right? So, which we are familiar with in classical thermodynamics and classical statistical mechanics. And therefore, we expect more of the classical result to be derivable, where this energy is dominant, right? This energy scale is dominant compared to the new energy scale. So this is a very heuristic argument, but I think what I'm trying to say is because what is this epsilon new energy scale? We don't know, right? So it's something that is not in classical mechanics. So therefore, we want to wash it out somehow. And the way that you should wash it out is when, it couldn't, it's possible that that's not how nature worked. It could have been possible that it was the inverse, that it was somehow a very, very high energy scale, which was irresponsible. But that is not the case. In this case, the new energy scale is a small energy scale, related to the thermal energy scale. So, this is not weird. It's just like it's just saying we're taking the thermal energies to be very large.
I was considering the t with a real physical system like on Earth, where t is, I mean, not that big.
Well, but in the black body radiation, T is quite big. In experiments, it's 2,000, 3,000 degree Kelvin.
Oh, understood.
Whereas the quantization energy of an atom is of several electron volts.